This is an application of root function. So in this problem, we have a hunter and he is at the edge of a riverbank and wants to get to his cabin. Okay, now the cabin is 4 miles if we travel directly north, but that's along all of this yellow in here. That's all rocky ground. And then 8 miles if he traveled west along the riverbank. So it's easier traveling on the riverbank. You can go 5 miles per hour on the riverbank, but it's rougher and harder on rocky ground, so you can only go 3 miles an hour. So the question is, he wants to get to the cabin. So what is the amount of distance along the river before he cuts and goes diagonally through the rocky ground? So we want to minimize the time it takes him. Okay, so obviously he could, if he wanted to, just travel along the riverbank and then head north. So it's going to be a long trip that way because we have to go 8 miles and then plus the miles north. So that would be 12 total miles. But if we're trying to find the time it takes, we use distance equals rate times time. Okay, dividing both sides by rate, what we get is that the time is equal to the distance divided by the rate. All right, so he does have the option of going 8 miles, and the rate that he travels going along the riverbank would be 5, and then he could go 4 miles through the rocky ground directly north, and he's traveling at 3 miles per hour. And so getting approximations there, 8 divided by 5 is 1.6, 4 divided by 3 is 1.33, so that would be about 4.933 hours. Okay, so that would be if he did the full 8 miles along the river, 4 miles north. Let's just kind of play around. What if he just went directly, I just want him to go directly through the rocky ground. That's definitely the shortest distance. So if he did that, this is 8, this is 4. The diagonal, we can use Pythagorean theorem. The diagonal there would be the sum of the squares of the shorter legs. Okay, so he would have a distance there of square root of 4 squared plus 8 squared. And so that would be the square root of 16 plus 64. Okay, so if he traveled that way, he has to go square root of 80, which is approximately 8.9 miles. So that would be, that's a lot shorter. This one is a total distance of 12 miles. This one is the square root of 80, which is 8.9 miles, which is good. But let's see how long it takes him. Okay, so he's going directly through the rocky ground, and he can only travel 3 miles an hour there. So that is approximately, let's see, square root of 80 divided by 3 is approximately 2.98 hours. Okay, so that's a better way to go. But is there even a best way where he gets a little bit of this quicker along the river and then some of the diagonal? So that's what we're trying to decide. Okay, so what I'm going to do is I'm going to write an equation that has to do with his time. Okay, we're going to use this fact that time is equal to the distance divided by the rate. Okay, so time is distance divided by rate, but what we're going to just try to do is minimize the time. So we're going to have him traveling along the riverbank for part of his trip, and then we're going to have him traveling on rocky ground for part of his trip. Okay, so I'm going to have this, I'm not sure yet when I want him to turn. I'm going to let this little bottom of that triangle be x. Okay, so what he has to travel, remember that the whole thing is 8. So if we subtract 8 minus x, that would be his amount of trip that he's going along the riverbank. Okay, And then this diagonal right in here, we're just going to use Pythagorean theorem. That would be 4 squared plus x squared. So those are his distances. Distance along the riverbank is 8 minus x. Okay, so we've got x is the base of the triangle, 8 minus x, that's the distance along the riverbank. Okay, now we just use the Pythagorean theorem. We found the distance that he goes on rocky ground. So we're going to plug those in. So we have distance on the riverbank, that was 8 minus x, and his rate on the riverbank is 5 miles an hour. Okay, next we're going to have, oh, I'll do those in blue because that's on the river. Okay, so there's his distance on the river, or his distance on the riverbank is 8 minus x, and he's traveling at 5 miles per hour. Okay, good. Now we're going to have him going along his rocky ground. So that is square root of square root of 4 squared plus x squared. So that would be square root of 16 plus x squared. But he can only travel 3 miles per hour on that rocky ground. Okay, so there's our equation for the total time that it takes. And we're thinking maybe there's something faster than what we had come up with, which was 2.98, just going directly through the rocky ground. So let's see. I'm going to go ahead and graph my function and then look at the minimum there. Okay, and the minimum is right here at x equals 3. So if I plug x equals 3 into my equation, I can find the distance that he goes along the riverbank. That would be 8 minus x, so 8 minus 3, which is 5. So if he travels 5 miles along the riverbank, okay, and then he heads towards the cabin, what we get is a time of 2.667, and that is less than just going directly at a diagonal towards the cabin. So we've minimized his time, used the benefit of him getting a little bit of that faster riverbank travel, and then going over rocky ground for just part of the trip. And there we've got it.